just rejoin. All right, now let's look at 10.2. So previously we have seen 10.1 progressive wave. So progressive wave is a wave that is moving. Okay, so a wave that is moving, the things that we focus on, okay, there are two things. First is the wave as a whole. Okay, you're looking at the wave as a one object. So you see how it moved, whether it moved to the right or it moved to the left. Okay, so the directions plays a very important roles because it affects the sign convention in your equations. So if you have a positive sign, then it means your object is shifting to the left. If you have a negative sign, then it means the object is shifting to the right. Okay, so this one, you use a negative sign in your equations. Y equals to a sine omega t minus kx. Whereas if your object is moving to the left, then the equations would be y equals to a sine omega t plus kx. Okay, so the difference is in terms of the sign. So you need to know the directions of the wave, okay, if you want to form an equations, because the sign is being determined by the directions. And of course, this is if you're looking at it as a whole. Okay, you're looking at the whole wave, how it moves, how it propagates to the left or propagates to the right. If you want to look at it in terms of particles, this wave actually is being formed by a series of particles. Okay, so what happens is now you drop something, let's say you drop something onto the water, let's say this is the stone. So it brings energy, okay, because you drops it. So from a potential energy, maybe it becomes a kinetic energy, and all this energy is being transferred to the next particles, okay, to the particle next to it. So particle next to it will start to oscillate. Okay, it's oscillate up and down or back and forth. It depends on the types of the motions that we're looking at. So there are two types of wave. One is a longitudinal wave, where the particle is oscillate back and forth, and one is a transverse wave. The particle is oscillating up and down. Okay, so in our examples here, I'm going to focus more on the transverse wave, okay, because it's easier for you to see what is the difference when you treat the wave as a whole and when you treat it as particles. So if you treat it as particles, what is happening right here? Now this object is oscillate, okay, it's oscillate in a periodic motion. Therefore, we can actually say the particle is moving with simple harmonic motion. So basically, you can use the equations from chapter 9 to solve what happens in a particles. But if you look at it as a whole, okay, then you're treating it as a wave. So the wave, okay, the wave, you have to solve it by looking at the various situations. Okay, that's why if you look at the equations in questions 1, you have the y1 and then they put x and t in the bracket. So if you're looking at it as a whole, then this wave actually it depends on these two things. Okay, it depends on the distance and also it depends on the time. At a different distance and at the different times, okay, the shape of the wave might change. All right. So okay, now this is if you're looking at a progressive wave. That is what we have seen in a 10.1. Now, how about 10.2? 10.2, we are looking at the standing wave. Now, what does it mean by standing wave? Standing wave is when you have two waves, okay, coming from an opposite direction. Okay, they are coming from an opposite direction, and then they superimpose with each other. Superimpose, in other words, you can say they are overlapping with each other. Okay, so when they're overlapping, what is happening is that now their amplitude add up. So if initially you have just amplitude here, so when they overlap with each other, okay, they become a much greater wave. Okay, they becomes a much greater wave. Right, so now instead of A, it has a 2A of amplitude. Right, they have a 2A's of amplitude. And then, okay, now because these two waves, okay, they are superimposed each other, and because of they met various conditions, now they are forming a standing wave. Okay, so for example, now you have a guitar and then you plug a string. Okay, so when you plug it, you are generating a wave in one direction, and then it is being reflected towards the other direction. Okay, it's being diffracted towards the other directions. So this process, it keeps happening. Therefore, now the wave, it seems like it is not moving. Therefore, we call it standing wave. So standing wave, you have another wave that is propagating, that is oscillating in the opposite directions. And then the two of them, they seem like they are not moving. Okay, they are not moving because of one going to the right and the other one is going to the left. So this is what we are going to look at today. So what is the relationship between the progressive wave and also the stationary wave? So in the progressive wave, we have equations y equals to a sine omega t plus kx, or y equals to a sine omega t minus kx. In a stationary wave, okay, because now you're combining both of them together, so basically you're adding these two equations together. Okay, y1 and y2, you add them up. And then when you add them up, you're going to obtain a new equations called y equals to a cos, okay, a cos kx sine omega t. So this is the equation for standing wave, the general equations, okay, the general equations for standing wave. Okay, now this equation is a slightly different than the equation from progressive wave. Now, what is the difference? Obviously, is in terms of the amplitude. Because the standing wave is coming from the superpositions of two progressive waves, so it has a larger amplitude. So the amplitude right now, okay, the A here, the purple color A, okay, is actually equals to 2 small letter a. Well, this small letter a is actually our capital letter A in this red color equations, okay, in a progressive wave equation. Okay, so most of the time, if in the questions you need to use both progressive wave equations and also stationary wave equation, for progressive wave, we use small letter a to represent its amplitude. Whereas we use capital letter A to represent the amplitudes of a stationary wave. If you have to use two equations, two types of wave, you are going to look at two types of the wave in the same equations. If the equations only have progressive wave, then it's up to you whether you want to use capital letter A or small letter a. Okay, but when you have two equations in the same equations, in the same questions, or you have two types of wave in the same questions, then we use different letters to represent the amplitude for progressive wave and also stationary wave, so that we can tell which A belongs to progressive wave and which amplitude belongs to stationary wave, right? So that is the things that you have to keep in your mind. If you have two equations, if you're going to use the dimensions, the general equations in the same questions, then make sure you use different symbol. One capital letter A, one small letter a. But if the question just one of the wave, okay, or it just involves one of the wave, then you can just use capital letter A. All right. Okay, so basically we have three types of amplitude in this 10.2 in this subtopic. First amplitude is what I told you just now, the small letter A. Small letter A is the amplitude, okay, amplitude of progressive wave. Okay, progressive wave. And then we have capital letter A is the amplitude of standing wave. And then, okay, and then we have one more thing called A cos kx. Okay, now what is the difference between A cos kx and also A? So I believe I've mentioned it to you before. Okay, I've mentioned it to you in a lecture. So the capital letter A, it represents the amplitude of the stationary wave. And when it comes to A cos kx, okay, when it comes to A cos kx, it represents the amplitude of, okay, amplitude of what? Amplitude of the particles. Okay, amplitude of the particles in the stationary wave. Okay, in a stationary wave. Now, why is it important to know what is the difference between A and A cos kx? So if you have a stationary wave, basically every particles in the wave, they have their own amplitude. And it can be calculated by using A cos kx. So you will have a different value. So for example, now let me draw the diagram again. Okay, so this is our stationary wave. I'm going to use a larger diagram so that you can see the difference. Okay, so this is our stationary wave. Okay, so another one is in the opposite directions, of course. Okay, so I'm lazy to draw it, so I'm just going to show it like this. So when it comes to capital letter A, okay, so this is our equilibrium position. Okay, so yeah, here got segment a bit. So when it comes to equilibrium position, so oops, this is what we say y is equals to 0. Okay, because it's equilibrium positions. Now, if we talk about capital letter A, then we just have one value, which is the amplitude of the wave. You're looking at it as a whole. Okay, you're looking at it as a whole. But when it comes to the amplitude of particles, now, every particles along the wave, they all have different value. Because like I told you just now, this is a stationary wave. It seems like they are all not moving. So every single particles, they are actually staying at their own amplitude. Okay, their maximum distance from the y equals to 0, from the equilibrium position. And all this green color line, okay, all this amplitude, the amplitude of each individual particles can be calculated by using A cos kx. Okay, so this is the amplitude of the particles. So that is the main difference between the A and A cos kx. So how do I know that A cos kx is the amplitude of the particles? Well, because I told you just now, particle is moving in the simple harmonic motion. So when it comes to simple harmonic motions, we have y equals to A sine omega t. So when you compare these equations with the equations in this purple color box on the left-hand side, you can see that this whole part, okay, this whole part, A cos kx is actually equivalent to the A in our simple harmonic motion. Okay, so therefore, this is the amplitude of the particles, right? Amplitude of the particles. So that is the main difference. So you need to know which amplitude you are looking at, whether you are looking at the amplitudes of a progressive wave, or you are looking at the amplitude of a stationary wave, or you are looking at the amplitude of the particles in stationary wave. Because stationary wave, every particle is always moving at its own amplitude, okay, staying at its own amplitude. So that is a summary for 10.2. Okay, so the main things I want to stress on, I want to tell you, is the difference between stationary wave and progressive wave. All right, now let's go back to the questions. If you look at this question, okay, yeah, let me draw a line first. If you look at questions 1, questions 1 now, it gives you two harmonic waves are represented by the equations below, where y1, y2, and x, they are all in cm, and t is in second. So if you look at these two equations, they are progressive wave equations. Okay, why? Because by just looking at the format, so it's actually coming from y equals to A sine omega t plus kx, and also y equals to A sine omega t minus kx. So you are given two progressive wave equations. Now what the questions wants you to write an expression for a new wave when these two progressive waves, they superimpose with each other. So when they superimpose with each other, they will give you a stationary wave. So what you need to know is the general equation for stationary wave. And like I told you just now, because now we have two different types of wave in the same equations, therefore I'm going to use small letter a for my progressive wave, okay, to represent the amplitudes of a progressive wave. Okay, so now let me write down the equations for stationary wave first. Y equals to A cos kx sine omega t. So when it comes to these equations, if you remember, I did tell you before, okay, in these equations, the constant variable is the amplitude of the wave. Because you have only one wave, the wave is not moving, therefore the amplitude of standing wave or the stationary wave is always fixed. And the second constant variable is the k. Okay, the wavelength won't change, right? If you have a constant wavelength, constant lambda, then k is also constant. And the last one is the omega. Okay, so the period is the same, the frequency is the same, therefore you have a constant angular velocity. So these three variables, they are constant. Okay, and k and omega you can obtain from the equations above, from the progressive wave equation, just by comparisons. So by comparison, okay, by comparisons, we obtain omega equals to pi radian per second. And then we also obtain k is equals to 2 pi. Now, what is the unit? So the unit, it follows the units of x. Now your x is in terms of cm. Therefore, k is a cm negative 1. If your x is in terms of meter, then k would be meter negative 1. Okay, m negative 1. So by comparisons, we have omega and we have k. The things that we don't have right now is the amplitude. But what we do know is capital letter A, the amplitude of a stationary wave, is equals to 2 times of the small letter a, which is 2 times of the progressive wave, the amplitudes of progressive wave. Okay, because when they superimpose, their amplitude add up. So the amplitude add up, now you have 2 times of the small letter a. So it is equals to 2 times 5, which is then equals to 10. So 10 cm. Units of A, it follows the unit of Y. So Y is in terms of cm, therefore A is in terms of cm as well. So now that you have omega, you have k, you have A, you can then solve questions 1. Okay, so you plug everything into the equations and eventually you obtain the answers given here. So Y is equals to 10 cos 2 pi x sine pi t. So of course, you will tell me you know the answer already. Can you straight away write down the equations? Y equals to 10 cos 2 pi x sine sine pi t. No, you have to show, okay? You have to show what is the values for pi, and you have to show what is the values of k, and you have to show how you obtain A, capital letter A, okay? So in exam, you cannot just give the final answer without showing the step, without showing why did you obtain all this value, how do you get all this value, especially A, okay? Especially A. How do you know it's 10? So you need to show it, okay? So kadang-kala pelajar akan beritahu saya, okay, saya tak tahu dah jawapan ini, so saya tengok saja, bolehkah saya terus tulis jawapan? Okay, no, you have to show, okay? Kamu kena tunjuk, because step ada marker, alright? Step ada marker. So that is questions 1A. So now let's look at questions 1B. Okay, let's look at questions 1B. So questions 1B determines the wavelength and also the frequency of the stationary wave. So how to calculate wavelength and frequency? Well, always remember, when it comes to chapter 10, there are 2 big families in this chapter. The first family consists of omega, period, and frequency. This is one big family. And then we have a second family in chapter 10, which is k and lambda. They are one family. Okay, so now you have 2 family in this chapter. So whenever a question is asking for example, wavelength, you try to see, okay, are you given any information about wavelength that can be used to find the wavelength, especially k? If you have k, then you can definitely get an answer. Okay, you can definitely calculate the wavelength. And then when it comes to frequency, now you try to think, okay, is there anything that you can use to determine frequency? Well, is there omega given? Is the period given? If this either one is given, then you will be able to determine the values of frequency. Okay, you should be able to determine them because they are one family. As long as you have one of the family members, then you will be able to determine the value for the rest. Okay, now let's see wavelength. Question asking for wavelength, and then we know that k is equals to 2 pi. Okay, 2 pi cm negative 1. And we know the relationship between k and lambda is k equals to 2 pi over lambda. So rearrange equations, lambda is equals to 2 pi over k, which is equals to 2 pi over 2 pi, and therefore you will obtain 1 cm. Okay, so how do I know it's a cm? Because k is cm negative 1, so lambda will have the same unit. Okay, lambda will have the same unit. Then how about frequency? So now we have, okay, if you look at this family, now the members that we have is the omega. Okay, the known value that we have is omega. So omega equals to pi radian per second. The relationship between omega and f is that omega equals to 2 pi f. Rearrange equations. Okay, f equals to omega divided by 2 pi, which is pi divided by 2 pi, and therefore you have 0.5 hertz. Okay, you have 0.5 hertz. So that is the answer. And of course, if you don't want to write it as hertz, okay, the unit can also be written as negative 1. Okay, both are correct. Okay, both are correct. So it's up to you whether you want to write it in a hertz or you want to write it in a as negative 1. So that is how you solve questions 1. Basically, it's just a very simple question. Okay, we spend quite a lot of time on this question because I want to go through the summary with you guys because the summary is important. Okay, so now I give you 5 minutes to write down the short notes, okay, as a form of revision. Make sure you understand what is the difference between 3 different types of amplitude, what is the general equation for progressive wave, what is the general equation for stationary wave. Okay, so 5 minutes for you to write it down, including the answer, before we proceed to the next questions. So now let's see. Questions 2. Okay, so these questions, I hope everyone's understand. Okay, if you have any questions, make sure to ask before I proceed to the next questions. Right?
All right.
We good today, so energetic. All right, now questions 2. Questions 2, a stationary wave is represented by the following expression. So as usual, whenever you are given an equations, the first things that you need to do is to compare it with the general equations. So this is a stationary wave equation. Therefore, the general equation should be y equals to a cos kx sine omega t. Okay, a cos kx sine omega t. So by comparison, we have three informations, which is a is equals to 15. So 15 is in terms of a cm. Because according to the questions, your y and x, they are in cm, and t is in second. And then the k, 0.5 pi means it is a pi over 2. Okay, pi over 2, cm negative 1, because my x is also in centimeter. And then the last one is omega. Okay, omega, it is equals to 5 pi. 5 pi radian per second. It is also coming from comparisons. Okay, by comparisons, we have these three pieces of information. So now questions 1. Find the three smallest value of x correspond to nodes. Okay, so now when it comes to this question, the things that you need to know is where is node and where is anti-node. Okay, and how are we going to find the value? So now let's see. So when you have a standing wave, okay, so this is the wave, and then standing wave, of course, you will have two, okay, one going, one coming back. So they form a wave that seems like it is not moving. And then nodes represents the place where they experience total cancellation. This is when your y is equals to 0. Okay, so here at this point, you have node, 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 and node. Okay, and then you have an anti-node at the maximum amplitude. This is your anti-node. Okay, anti-node, anti-node, and anti-node. Now, if you look at this diagram, there's one very important information here, where it shows you the distance between two nodes and also the distance between two anti-nodes. They are equals to half cycle. Okay, they are equals to half cycle. So why is it important to know that they are equals to half cycle? Okay, wait, yeah. Where is my pen? Okay, here. So they are equals to half cycle means they are equals to pi radian. Okay, they are equals to pi radian. Or you can also say they are equals to lambda over 2. Depends on the questions. If the questions ask you to determine the lambda, then you know the distance between them is lambda over 2. If the question asks you to determine the angles, then you know it is pi radian. Okay, so this is a very important information. Okay, it tells you the shortest distance between two consecutive nodes and between two consecutive anti-nodes. And how about the distance between nodes and anti-nodes? So if you look at this diagram, the shortest distance between a node and an anti-node, okay, is from here until here, which is lambda over 4, okay, just 90 degrees, okay, 1/4 of the complete cycle. Okay, or you can also say it is the equals to pi over 2 radian. So in terms of whether you're looking at the angular displacement or you're looking at it in terms of the wavelength, okay, in terms of the wavelength. So now what we want to do, we want to calculate the positions of nodes and also the positions of anti-nodes. So what does it mean by positions? Now you want to calculate the horizontal distance. So when it comes to a progressive wave, we have types of the graph which is y against x, right? y against x. So now what we want to find is the values of x. We want to find the positions of nodes and empty nodes. If you are given an equation y equals to 15 cos pi 0.5 pi x sine 5 pi t. So how are we going to solve it then? We want x, which means we want this value. Okay, we want this value. The x is here. The x is located at the first part of the equations. So in that case, the only known values that we have right now is that, okay, at empty nodes or at nodes. Now let's look at nodes first. At nodes, okay, where you have y equals to 0, when your y equals to 0, our A, okay, our A, now let's just write it, the amplitude, A cos kx, our amplitude of the particle is equals to 0. That is what happens at nodes. Okay, so this is a known value because we cannot look at the whole equations. Okay, the equations has a whole because we don't know the time. We are not given the time. We don't have any information about the times and the positions given. Okay, we are not given the positions. We are not given the time. That's why we cannot straight away apply the first equation. But what we do know, at nodes where the wave, two wave, they experience total cancellation, the amplitude of the particle located at node is equal to 0. Okay, they are not vibrating at nodes, so the amplitude is equal to 0. So this is the equation that we want to use to determine the values of x. So can we determine the value of x? Obviously we can, because we have the values of k already. Okay, and if you rearrange the equations, okay, then we obtain cos kx is actually equal to 0. Okay, cos kx is equal to 0. And then kx, k we have 0.5 pi, which is pi over 2. Okay, so kx we have a pi over 2. So this is our, okay, now I'm going to skip it first. Okay, I'm going to skip it first. I will substitute it at the last step. So kx is then equals to cos negative 1, 0. Okay, cos negative 1, 0. So what am I going to do right here? I want to calculate the values of cos negative 1, 0. Okay. If you calculate the values, if you use calculator and press cos negative 1, 0, then you will obtain kx is then equals to 0. Right? So that represents the positions of your first node. Okay, so which means at this point, okay, your graph is actually look like this. So the first node is happening at kx equals to 0. Okay, but if you look at the question is asking for the distance that is greater than 0. So 0 obviously is not the right answer, right? But what we do know, if you look at the diagram again, the distance between nodes and nodes, it is equal to pi radian. Aha, so that is very important. That is very crucial. So distance between nodes and node is pi radian. If the first node located at x equals to 0, then the following nodes, the second node would located at pi radian. Okay, it located at a pi radian. And then, okay, cos negative 1, cos negative 1, 0. Okay, cos negative 1, wait, yeah, let me calculate. I think I pressed the wrong button.
90 meter.
90 kan? Oh, patutlah saya rasa pelik. Okay, so thank you. Okay, so cos negative 1, 0 is 90 degree, which is pi over 2 radian. Okay, so my bad. So pi over 2 radian. Okay, so this first value is fine. But if you look at the question is asking for 3 smallest. Okay, 3 smallest value. So which mean, okay, pi over 2 itself is not enough. You need the following position. So the first position, okay, the first one that we are going to use, the first position that we're going to use is pi over 2 radian. And now we know the following one, okay, the distance between the first and the second node is pi radian. So you just add pi. So for the second node, it is located at pi over 2 plus pi. Therefore, the second value here, it should be 3 pi over 2 radian. Okay, 3 pi over 2. And if you keep moving on, okay, you look at the next, and again, the next node, the third node in my diagram. Exactly, good. So what is happened here is now becomes 3 pi over 2 plus pi. Therefore, like your friend said just now, you have 5 pi over 2. So done, okay? So you just need to state 3 because question is asking for 3 smallest value. Sometimes, I think in the past year questions, one of the questions actually asking for 5, if I'm not mistaken. Then you have to keep adding pi until you get the 5th value, right? So since this question is asking for just a first 3 value, then that is what you should do. Okay, but that is not the end yet. Okay, that is not the end yet. So if you look at the questions, okay, if you look at these questions, now you have kx right here, right? You have kx right here. So what you need to do, you need to rearrange the equation. So we have kx equals to pi over 2 radian. Therefore, if you sub it into the equation, so you have pi over 2, and then here is x equals to pi over 2, and then 3 pi over 2, 5 pi over 2. So you rearrange the equation, therefore x is equals to 1 cm, 3 cm, and 5 cm. Okay, you divide it. Pi over 2 divided by pi over 2, they give you the first value, which is 1. And then 3 pi over 2 divided by pi over 2, you obtain 3 cm. 5 pi over 2 divided by pi over 2, you obtain 5 cm. So you rearrange the equations, and therefore now you obtain a final answer, which is x equals to 1 cm, 3 cm, and 5 cm. Okay, and 5 cm. So the reasons why I know it's in cm, because my k is in cm, because my x is in cm, according to the questions. Okay, x in cm, k is also in cm. Therefore, the final answer is in cm. So that is for nodes. Okay, that is for nodes. How about antinode? So when it comes to antinodes, the information that we have is a cos kx equals to, now it's no longer equals to 1 and no longer equals to 0, it is equals to a. Okay, because antinodes, it happens at the amplitude of the wave, of the stationary wave. Therefore, we know for the particles that is located at the positions of antinode, okay, it is equals to a. So rearrange the equations. You have cos kx equals to 1. Rearrange the equations again. Kx equals to cos negative 1, and then this is 1. And you will obtain 0. So now that you have a 0 here. And again, if you look at the question is asking for value that is larger than 0. So you need to state, you need to find out what is the following 3 value. You need 3 more value here, because 0 is not our answer. Okay, even though according to the calculation, kx is equals to 0, but that is not the final answer. You need to add, okay, you need to find out the position for another 3 antinodes, because questions won't accept 0 as the final answer. So we know, according to the diagram again, okay, according to our diagram again, the distance between antinodes and antinode is equals to pi radian. So what are you going to do? You just keep adding pi radians again. So first value is 0. The following value would be pi. And then you have 2 pi. And then you have 3 pi. And so on. Okay. So since our k is pi over 2, so pi over 2 times x is equals to, now we can exclude 0 because questions doesn't want 0 as our final answer. So pi, 2 pi, and 3 pi. Right? And then rearrange equations, you should obtain 2 cm, 4 cm, and 6 cm. So that is our final answer. Okay, that is our final answer. So that is how you solve it. Okay, so that is how you solve it. The crucial part, the most important thing is you know the shortest distance between 2 consecutive nodes and the shortest distance between 2 consecutive antinodes. Okay, 2 consecutive nodes and 2 consecutive antinodes. So that is the answer for questions 2A. So now I give you 3 minutes to write it down. Okay, to write down the diagrams, to write down the questions, and then to make a short note for yourself. Make sure you understand this question. Okay, 3 minutes from now. Before we proceed to questions B. Questions B is just very simple. Okay, so soalan ini diagram yang penting. Pastikan Anda ada catat diagram. Okay, sebab diagram tunjuk Anda kenapa saya tambah pi. Okay, kenapa saya tambah pi untuk setiap satu nilai. So it's actually is keep adding pi. Okay, so now let's look at questions B. Questions B is just very simple. Just make sure you read the questions carefully. So question is asking for amplitude of particles. Okay, amplitude of particle, not amplitude of progressive wave, not amplitude of stationary wave, but the amplitude of a particles, which means the equations that we're going to use is A cos kx. Okay, so that is the equations that we're going to use to solve questions B. So B1. Okay, so amplitude of particles. So you just write down the full statement in your exam. Okay, amplitude of a particles equals to A cos kx. So given A, okay, by comparisons, A just now is a 15 cm. So 15 cos k is pi over 2, given x 0.5 cm. So you just plug in the value. Okay, you just make sure your k and x, both of them, they have same unit before you substitute it into the equations. All right, so the crucial part is k and x, should have a same unit. So you plug it in, and then you just press your calculator, and eventually you will get 10.6 cm. So for our questions 2, you just repeat the same thing. Okay, you just repeat the same thing. So AOAP. So 15 cos pi over 2 times 1.1. So it is equal to negative 2.35 cm. Questions number 3, amplitude of a particles is equals to 15 cos pi over 2 times 2.2. So it is equals to negative 14.3 cm. So for our first one, when x equals to 0.5, your particles is located at a positive y-axis. And for the questions 2 and 3, because you have a negative value, means that they are actually located at the negative axis. Okay, negative axis. So that is. So just a very simple questions. All right, so 1 minute for you to write it down, then we will proceed to the next questions. So next question is just a very simple. If you want to try, you can try first. Okay, as long as you understand the diagram given in a questions 1. Okay, in a questions A, then you should be able to answer next questions. All right. So now let's look at questions 3. Question 3 is just very, very simple questions. So a transverse wave travels along a stretched string at a speed. So you are given speed and the frequency 200 hertz. Stationary wave produced on the string. Determine the distance between two adjacent nodes. So, well, if you understand the diagram above, for two adjacent nodes, the distance between them is lambda over 2. Okay. Whereas for the following question, the distance between a node and an antinode that is nearest to it, the distance is just a lambda over 4. So if you understand this concept, then straight away you can solve the questions. But of course, you need the lambda first, right? So now you have a transverse wave. So wave speed given v is equals to f lambda. So lambda is equals to v divided by f. So 8t divided by 200, which is equals to, 2 over 5, 0.4. Okay, 0.4 meter. So lambda equals to 0.4 meter. So questions 8, two adjacent nodes. So between nodes and nodes, the distance is lambda over 2. Therefore, 0.4 divided by 2, it is 0.2 meter. For questions B, the distance between a node, okay, a node and an empty node, we know it is equals to lambda over 4 according to the diagram. Therefore, 0.4 divided by 4, it is equals to 0.1 meter. That's it. Okay, that is how you solve it. Very simple. Okay, very simple. Okay, so again, 1 minute for you to write it down. And then, let's see. Okay, the next one is the sound intensity. Okay, let's take a short break. We will continue again at 15 past 3. Okay, 3 suku kita sambung balik. Kita rehat sekejap. Make sure you complete this exercise. And then at 3:15, we will proceed to exercise 3. New subtopic. Okay, sound intensity. So let's take a short break. All right. So far, any questions before we proceed to the next subtopic? No. Very good.
Oh, madam,
Buka
are you
mic.
open the mic?
Yeah, I just noticed. Thank you very much.
Welcome.
Okay. So basically, in this subtopic, when we talk about sound intensity, now sound intensity, it determines the loudness of a sound. Higher intensity means it's louder. Okay, and then the frequency determines the sharpness of your sound. Okay, so if you have a very high pitch sound, then it means it's a very high frequency. But if you have a very loud sound, means you have a very loud, very large intensity. So I equals to P over A, and P is the power. A, you have to be careful. There are two different A in these equations, in this chapter. One is amplitude, but this A is not amplitude. It is area. Okay, it is area. Area of what? Area of sphere. Okay, because when you talk, when someone is talking, when you generate sound, when sound is being produced, it's traveling out in all directions. So all directions means including front, back, up, and bottoms. Okay, it's all direction. So it is a sphere shape, a spherical shape. So area for sphere, it is equals to 4 pi r squared. Okay, not area and then not a circle. So this is a very common sin misconception. Okay, because on paper we can only see circle, but in reality, sound is traveling out in all direction. Therefore, it should be a sphere shape. Okay, spherical shape. Okay, now let's go back to energy. So P equals to E over T. Okay, and when it comes to sound, actually you are looking at particle. This particle, okay, let's say this is the sound, okay, the speaker. So speaker generates sound, and then all these particles, they will start to vibrate back and forth. This is a form of longitudinal wave, okay, while the particles vibrate back and forth. So when it vibrates, this is actually a periodic motion. Okay, this is actually a periodic motion. Therefore, energy can actually be calculated by using the equations of simple harmonic motion, because your particle is oscillating. It's moving in a periodic motion. So it is 1 over 2 Ka squared. That's why when we talk about this A, when we talk about equations between P and amplitude, I and amplitude, we say they are directly proportional. Why? Now let me plug in these equations and these equations into the equations of intensity. So I is then equals to E divided by T divided by 4 pi r squared. Okay, and then it is equals to my E is 1 over 2 Ka squared. So 1 over 2 Ka squared divided by 4 pi r squared T. Okay, and then, okay, I can just leave it like this, because what I want to show you is just a relationship. So the things that you have to be careful is the A here. This A is no longer represents the area, but now this A is represent amplitude. Okay, it represents amplitude of the particles. So in the initial equations, the A in the equations of intensity, in the definitions of intensity, it represents the area. But if you expand the equation, then you will have another A in the equations, which represents the amplitude of the particles. Okay, the amplitude of the particles. Okay, now when it comes to this A, now why is it important to know this the second A? These equations, we seldom use it in calculation. We just use it to show the relationship. The relationship between I and amplitude, and the relationship between I and also R squared. So according to this relationship, this equation, my I is directly proportional to amplitude square. Okay, that's why you have this equation in your notes. So this is the first relationship that we can extract from the equations. And the second relationship that we can get from the equation is our I is inversely proportional to R squared. So which tells you I actually depends on these two things. Okay, it depends on the amplitude of the particles, of the vibrations, and also it depends on distance, whether it's located close to the object or far away from the object. And usually in the calculations, we will treat P as a constant value if it is coming from the same source. All right, so usually the changeable variable is the R, usually in our questions. Okay, I don't know whether there's an unusual situation, but most of the time in our questions, the things that we change is just the R. Okay, amplitude, usually we just use it to describe the relationship between I and amplitude. That's it. Okay, I don't think I have seen any questions that need you to use amplitude in the calculations yet. Not yet. Okay, but it doesn't mean it won't come out. Okay, not yet. So I equals to P over A. This is the equations that you must know. Okay, most of the time we use these equations in our questions. So power is a constant value if you are looking at the same source. That is the things that you have to know, because when it comes to this subtopic, the questions like to give you two different scenarios and then maybe ask you to determine the intensity or any other variables. Okay, but then you have same source. So same source means same power. Okay, same source means same power. So now let's see questions 8. Okay, questions 8. A loudspeaker radiates sound wave uniformly in all directions. So this all direction means spherical shape. Okay, spherical shapes. At a distance 5 meters, so you are given R. The intensity given is 0.35 watt per meter squared. Calculate the power of the loudspeaker. So this is a very straightforward questions where you have I equals to P over A. Given I is 0.35 and then P divided by, now you are given a distance. Okay, so you have a R. So A for spherical shape is 4 pi R squared. So plug in the value. 0.35 is equals to P over 4 pi 5 squared. So P is then equals to 110 watt. Okay, 110 watt. Now questions B. So questions B, this is what I told you just now. Now you're still looking at same source. You're still looking at the same loudspeaker. You're not changing anything. Okay, therefore, it will still have the same power. So what you want to calculate now is the sound intensity at the distance of 7 meters from the source. You have the same source. The only things that is changing in our situations, in our question, is the R, is the distance. So again, I'm going to use I equals to P over A. So I is the things that I want to calculate right now. So I'm just going to rewrite it. So P, okay, now P, because it's coming from the same source, therefore it is equals to 110. Okay, because the same source. You calculate it from questions 1 already. So 110 divided by 4 pi, now the R is a 7, so 7 squared. Therefore, my I is now equals to 0.179 Wm negative 2, okay, watt per meter squared. Okay, watt per meter squared. So a meter negative 2, that is because of questions give you distance in terms of meter. Okay, if questions give you distance in terms of cm, then this will be cm negative 2. So be extra careful with the unit. The safest way is to change everything into SI unit before you solve it. Right? So that is questions 1. I give you 1 minute to write it down because this is just a very short and simple questions. Okay, very short and simple questions. So the things that you need to know is the power. So just make a short note for yourself. Why the power is equals to 110? Because you are looking at the same source. It's coming from the same speaker. Okay, so now let's look at questions 2. Questions 2. A small source emits a sound wave with power output of 80 watt. So you have P here. Okay, find the intensity that is 3 meters from the source. So very simple question, very straightforward questions. I equals to P over A, which is I equals to P divided by 4 pi r squared. Okay, always 4 pi r squared because you have a spherical shape. So it is then equals to 80 divided by 4 pi 3 squared. So the answer is 0.707 Wm negative 2. Questions B. At what distance would the intensity be 1/4? As much as it is at r equals to 3 meters. So this question, actually r is an unknown. Okay, r is an unknown. So what are we going to do right here? We want to see at what distance the I is 1/4 of the original intensity. Now, what does it mean by 1/4? So it means you use the original value 0.707 times 1/4. So this would be our new intensity. Okay, so let's call this I1. Questions A, I'm going to call it I1. So questions 2, I2 equals to 0.707 times 1/4. So it is equals to, I don't have the value. So you calculate it. Okay, you calculate it. So Wm negative 1. Okay, so 0.707. 0.1768. Okay, 0.1768. Oops. 1768. Right, if you got it correct, this is the answer. Okay, so now that I have the I2, I want to calculate R, and it is still coming from the same source. So I2, again, it is equals to P, but now it's divided by A2. Okay, A2. So P is a constant variable, constant value. So it is equals to P over 4 pi R2 squared. Okay, the second R, the unknown, the R that we don't know. So now plug in the value. I have 0.1768 equals to 80 divided by 4 pi R2 squared. Rearrange the equations. Your R2 should be 6 meters. Okay, 6 meters, not 6 cm. Okay, the answer here is wrong. So it should be 6 meters. So question C. Find the intensity and find the distance at which the intensity of the sound is now equals to 1 times 10 to the power of negative 8. So basically, you just repeat the same thing. Okay, you repeat the same thing. Now you have what? You have a I3 equals to P over 4 pi R3 squared. So plug in the value, rearrange it. You should obtain R3 equals to 2.52 times 10 to the power of 4 meters. So again, still the same power, but now with different intensity. Okay, different intensity. So different intensity give you different R. All right, so 1 minute for you to write it down. Then we will move on. We will proceed to exercise 5. Okay, we will skip 4 first. 4 we keep it for Friday. Okay, exercise 4 kita skip dulu, kita simpan untuk hari Jumaat sebab dia susah sedikit. Dia memerlukan masa yang lebih banyak. So what are we going to do right now? We're going to look at exercise 5. Exercise 5 Doppler effect, just a very short and a simple topic. Okay, simple subtopic. So you write down the answer first before we proceed to exercise 5. All right. So exercise 4, skip dulu, okay, because I need a bit of time to go through them, to go through the diagram again. Now let's look at exercise 5, Doppler effect. Okay, Doppler effect, it's very simple subtopic. Okay. So we have a general equations, just one equation, where we have a F, now I'm going to call it O, equals to V plus minus VO over V plus minus Vs times with Fs. So the things that you have to know is the meanings of O. O represent observer, okay? Or we say the things that receive the frequency. Now, it could be a living object or a non-living object, as long as it is the part that is receiving the frequency. So keep that in your mind. Okay, that is a misconception among students, why they always thought that observer must be human. Not necessary. Okay, it could be any object inside the room. It could be any point inside the room, as long as it is the point that receives the frequency. And then S is the source, okay, the things that generate the sound. So the source, the things that generate the frequency. And then the VO and VS also the same. VO is the observer frequency. And then VS is the source frequency. Okay, how fast does it move? Is it moving? Okay, is the source moving? For example, a moving source would be a siren on an ambulance or a police car siren. Okay, so that is the examples of the moving source. And then the V without any subscript is the speed of sound, which is a constant value. Okay, speed of sound. So yeah, we have 3 different V. So as long as you understand what is the difference between them, then you should be able to solve the question. But the remaining thing would be how to determine the directions and how to determine the sign convention. So usually in your syllabus, you'll be given 2 different cases. One is when observer is not moving. So when observer is not moving, we say VO equals to 0 meter per second. Okay, observer not moving. Or we say stationary observer, okay, not moving. And then the other case is when Vs equals to 0 meter per second. So one of them must be 0. Okay, so this one, the source is not moving. Let's say your police car is not moving. You just park there, but you walk towards it. Then we have a non-moving source, a stationary source. Okay, not moving source. So 2 example, 2 case. Okay, so let's see how to determine the sign convention. So let's say this is you, the observer, right? And then this is a police car. Okay, this is a police car. So the police car just passed by you, and what happens right here is now you're not moving. Okay, so I'm just going to show you one example because this example can show you clearly how to determine the directions for all variables and also how to determine the sign convention. So first of all, now you have a non-moving observer where VO equals to 0 ms negative 1. So the things that we want to do right now is to determine the directions of Vs and also V. That is a part that students always confuse. Now, this is your source. Okay, this is a source. Source is moving towards the right-hand side. So your Vs right now is moving to the right, or we say moving away from the observer. Okay, moving away from the observer. So we have the directions of Vs. Usually that is not an issue. The issue is how to determine the directions of sound. Now, like I told you before, sound it's being emitted in all directions. Okay, now the sound is being emitted in all directions. Okay, but then what we want to do is we want to take the direction from the source towards the observer. So now my source is on the right-hand side, my observer is on the left. So the direction of the sound, I'm going to draw it from right towards left. This is the directions of the sound. So you don't look at all directions. Only one direction we want to use in our calculation. Okay, we only choose one direction. The direction is from source to observer. Okay, from source towards observer. So now my source is on the right, my observer is on the left, therefore the directions of the sound is from right towards left. Okay, so even though it should be a spherical shape, but when it comes to calculation, we just take one direction. Now, why is it so important to determine the direction? Because if you look at the summary notes given in your text, in your books, it tells you when VO or VS, so when VO or VS, it is moving in the same direction, in same direction with a V, then what happened? Then we use negative sign in our calculation, in our equations. Then we use negative sign in our equations. We choose negative sign. And then if your VO or VS is in opposite direction with V, then we use positive sign in our calculation. So one of the variable must be equals to 0. Like I told you just now, in your syllabus, one of the V must be 0, either VO or VS. Then the remaining one, you use these two rules to determine the sign convention. You try to check whether the remaining V is moving towards the same directions as the V or moving in the opposite direction with V. If it is the same, then you choose the positive sign. If it is the opposite, then you choose negative sign. So for example, in this diagram, I say VO is equals to 0, right? Therefore, my equations would be F naught equals to V over V plus minus VS and Fs. So this is the remaining term because my observer V is equals to 0. VO is equals to 0. And according to the diagram, my VS is going to the right and V is going to the left. They are opposite direction. Therefore, the equations would be F naught equals to V over V minus plus VS times with SF. So this is the equations that I'm going to use, if this is what happened. If this is what happened. So this is the equation that I'm going to use. So does it make sense? Try to think. Well, it is makes sense. Why? Because if you use V plus VS, it means your observer frequency would be less than your Fs. Your observer frequency would be less than your source frequency. And now, according to the diagram, the sound is moving away. Therefore, what the observer received, indeed, it should be less than the actual frequency, the real frequency, because it's getting further away. So actually, you can check your final answer with common sense, by using your common sense. So if your object is moving away, if they are getting further apart, then the frequency observed should be less than the actual frequency. If the distance between them is getting closer, then the observed frequency should be higher than the actual frequency, which is the source frequency. All right. So that is a quick summary for Doppler effect. So now let's move on to questions. So questions 1. Exercise 5, questions 1. The siren of a police car at rest emits a predominant frequency of 1,600 hertz. Now this one, it tells you the siren of police car at rest. It doesn't mean that the source is at rest right now. The purpose of this statement, the first statement, is to tell you what is the actual frequency. Actual frequency is the frequency that is being recorded when your source is not moving, when the source is at rest. That is our actual frequency. So that is one of the reasons why it tells you this statement. So it tells you police car at rest, it emits this frequency. So this would be our Fs. So Fs is equals to 1600 hertz. What frequency will you hear if you are at rest? Now you hear it. So you are the observer, and now you are at rest. So which means, according to this statement, now I have VO equals to 0 ms negative 1. And the police car is moving. So now my source is moving. Vs is equals to 25 meter per second. Okay, 25 meter per second. And that tells you Fs is 1600 hertz. Okay, so now it even is moving. It is the actual frequency is still 1600. Okay, just that it tells you if the police car is not moving, this is the frequency observed. So frequency observed when the source is not moving, that is the real frequency. Okay, frequency observed when object is not moving, when source is not moving, that is actual frequency. Okay, kalau kamu dengan source kedua-dua, both you and observer, okay, observer and the source, both of you are not moving, you observe the sound, you hear the sound, then that is real frequency. So kamu kena jangan confuse, okay, jangan confuse. Not that one of them is not moving. The reason, the condition is both of them, they are stationary. Observer and source. If both observer and source, they are not moving, then what you hear is the actual frequency. Okay, saya harap explain begini, then should be easier for you to understand. So Fs equals to 1600 hertz, and then VO equals to 0 ms negative 1, and your Vs is equals to 25 ms negative 1. So question asks you to calculate observed frequency. So FO is an unknown. Okay, and then given V is equals to 340. So like I told you just now, speed of sound is a constant value. Okay, it is a fixed value and will most of the times will be given. So questions A. What if the police car it moved towards you? So this is you. This is a police car. This is a siren. Okay, this is a siren. So what happens right now? Okay, your V is equals to 0. What we do know is the directions of sound. Okay, the V is always from source towards the observer. Okay, so questions A. Questions A, it tells you now, this police car, it moved towards you. So you have Vs towards you. So which means the equations that we're going to use right now, FO is equals to V over V plus minus Vs Fs, because observer is 0. Okay, so according to the diagram, FO is now equals to V over V. Okay, now because V and Vs, both of them, they are moving towards same direction. So we choose negative sign here, Vs. So when you use V minus Vs, then this equation, it will give you, okay, it will give you a case where your F naught is greater than Fs, which makes sense because now the sound is getting closer to you. It's moving towards you. Okay, therefore the frequency is higher. The observed frequency is larger than the actual frequency. So you plug in the value, you should be obtained F observer equals to 1726 times 98 hertz. Okay, times 98 hertz. So for second case, questions B. Questions B, if the police car it moved away from you, Vs moved away from you, then in this case, we have F naught equals to V over V plus Vs. Okay, because your V and Vs, they are moving towards opposite direction. So in this case, your F naught would be 1490.4 hertz. So it should be less than, because it's moving away. So FO should be less than Fs by common sense. So is it correct? Yes, because your Fs is 1600. So when it moved away, the value is less than 1600. If it moved towards you, the value is larger than, is greater than 1600. Okay, so from here, we know that our final answer makes sense. Okay, it makes sense. So that is how we check. So in exam, in case you got the opposite answer, then that means something is wrong in your calculation. Okay, if the object is moving towards you, but the frequency decreased, then something must be wrong. All right. So this part I give you, okay, because I'm including the summary and so on, I give you 3 minutes to write it down. Okay, I cannot give you too much time because my phone is almost out of battery. Oh, I think it cannot last until I finish discuss the second questions. Okay, never mind. Questions 2, we will keep it for a Friday. Okay, we'll keep it for Friday class. You can try it first. Right now, you just write it down. Okay, you just write down the short notes, the summary, and also the answer. So if you are done, then you may leave the class. That's all for today.